Good morning everyone, my name is Antarik Parashar. I am from the Department of Chemical Sciences and today I am going to present on the topic of chromium-chromium quintuple bond complexes. And this word quintuple actually means to have 5 bonds between 2 chromium centers. Now starting from our class 11th, we have been studying the different types of bond, and we know that in alkanes there exists only one bond between the 2 carbon centers, which is known as the sigma bond. In alkenes, there exists 2 bonds between the 2 carbon centers. One is the sigma and other is the pi. Similarly, in alkynes, we have been studying that there exists actually 3 bonds between the 2 carbon centers, and one bond is the sigma bond and the 2 remaining bonds are the pi bonds. But we have never ever seen 4 bonds between 2 carbon centers. This is essentially because during the formation of the 3 bonds between the 2 carbon center, one sp hybrid orbital is involved in formation of the sigma bond, and the 2 unhybridized orbitals that are left are eventually involved in the 2 pi bond formation. But to have 4 bonds between 2 carbon centers, there should be a possibility of 3 pi bonds, which is not the case. And in case of carbon, we do not have any more unhybridized p orbital left, or also we do not have any vacant or unhybridized d orbital left in this case, that will allow us for the formation of 4 bonds between 2 carbon centers. But in the world of inorganic chemistry, like for example in the case of metal clusters, we can easily observe compounds or complexes which have 4 bonds, 3 bonds, or in some rare cases 5 bonds between 2 metal centers. So today we are going to study a type of such case where there is the existence of 5 bonds between the 2 chromium centers. So before directly jumping into the topic, let us have a short revision of what are the different types of bond. We know that for the formation of sigma bonds, the orbitals must overlap in a head-on fashion. For example, the dz square orbital, if there are 2 dz square orbital, both the dz square orbital must overlap in this manner. This is called a head-on overlapping, and in such cases, along the internuclear axis, a sigma bond is formed. Now for the formation of pi bonds, we know that side-on overlap must exist. Now in such cases, the d orbitals must lie in this fashion and they must overlap in the side-on fashion. This is not, they will be moving in the internuclear axis, but the lobes will not be present in the internuclear axis. They will be present in an axis which is perpendicular to the internuclear axis. Similarly, we also have the case which is known as the delta bonding, and in delta bonding, the speciality of this case is this bond is actually perpendicular to the sigma bond. We are considering z axis as the internuclear axis, x axis and y axis, which are perpendicular to the z axis. So now if we consider the dx square minus y square orbital, so this is the dx square minus y square orbital, and we consider another dx square minus y square orbital here. So in this case, we can see that this lobe will overlap with this lobe, similarly this. So we can see that 4 lobes are actually being overlapped in this thing. This, with the help of these markers, we can actually imagine how this overlap is actually occurring. So these are 2 markers I am holding in this hand and 2 holding in this hand, and they will overlap in a facial manner in this way. Okay, so continuing with our topic. So this formation of delta bonds actually gives us the possibility of forming multiple bonds between the 2 metal centers, that is bonds which are higher in number than the triple bond, right? So today we are going to study a special case of such a compound. So firstly, I am going to draw the structure of this compound. So the structure of this compound is actually very beautiful. This is a chromium. I will be drawing the structure a little bit on the right side. So this is a chromium, 5 bonds present between the 2 chromium centers, and in the plane of this chromium we have a benzene ring, substituted benzene to be precise, and with this benzene we have another benzene ring which is perpendicular to the previous benzene. We have isopropyl substituents, as you can see. Similarly, in this side also we have another benzene perpendicular to this one with isopropyl substituent. Similarly, this whole structure is again present in the bottom with this chromium. So this is the structure, and there are some secondary interactions of this chromium with this ipso carbon center. These are secondary interactions. Similarly, this carbon also have some secondary interactions with this carbon center, this ipso carbon center, which stabilizes this overall molecule. Now, let me keep the structure aside, and now we will be studying the formation of this structure with the help of molecular orbital theory. Now we know that these substituents are actually similar to phenyl substituent, right? A carbon which is attached to a phenyl group, and we know that to calculate the oxidation state, we consider that the oxidation state of phenyl is -1. So in the similar case, we will consider the oxidation state of this whole substituent as -1, and this will give us the oxidation state of chromium to be +1. So we will write the electronic configuration of this chromium atom. Chromium +1. As we know, chromium has a ground state electronic configuration of 4s1 3d5. So the electron from the 4s orbital will be ejected out, and we will be left out with 3 d5 orbitals. 1, 2, 3, 4, 5. So one electron will be present in each of the d3d orbitals, right? Now, as we can see, this is dz square orbital, dx square minus y square orbital, dxy orbital, dyz orbital, dxz orbital. So we know that this dz square orbital will be contributing to the formation of sigma bond. Similarly, the other two orbitals which are actually present in the internuclear axis, that is the yz and the xz orbitals, will contribute us with side-on overlapping to form the pi bonds. And the rest orbitals which are not present in the internuclear axis, that is the dx square minus y square orbital and the dxy orbital, will overlap in a facial manner to give us 2 delta bonds. 2 delta bonds, right? So we have got 1 bond, 2 bond, 3 bond, and 2 pi bonds. That gives us a total number of 5 bonds between 2 chromium center. And let us now study the molecular orbital diagram of this complex to understand it in a better way. So we'll be studying the diagram for only the chromium atoms. So this is one chromium, this is another chromium. So 1, 2, 3, 4, 5. Let me draw this here. 1, 2, 3, 4, 5. And here 1, 2, 3, 4, 5. So firstly, there will be the formation of the sigma bond. This is the dz square orbital, dz square orbital, and they will overlap to form the sigma bond. This is the sigma, and this is the sigma star anti-bonding. Similarly, next we have the pi bonds, and we have already discussed that the pi bonds are formed between the 2 orbitals which are actually present in the internuclear axis, right? Therefore, dxz and dyz, dxz, dyz are going to be the going to take part in the formation of the pi bonds. So this will form the pi bonds. So pi. Now the remaining 2 orbitals, that is the dx square minus y square and the dxy. These 2 orbitals are going to take part in the formation of facial bonds, that is the delta bonds. Sorry, I have forgot to Right, the pi's are anti-bonding orbitals. Now, the last two orbitals are taking part to form two delta bonds. And these delta bonds are actually higher in energy than the pi bonds because of its unstable nature. Delta star. So we have got all our orbitals. Now we have left to fulfill the electrons. We know that each orbital contains one electron. So total there are 10 electrons present. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the sigma orbital, the 2 pi orbitals and the 2 delta orbitals are fully filled, and we get our molecular orbital diagram for this chromium-chromium complex. This is our MOT for this case. And to calculate the bond order, we have the formula. Bond order is equal to half into number of electrons in bonding minus number of electrons in anti-bonding. So in the bonding orbitals we have 10 electrons. In the anti-bonding we have no electrons. Therefore it gives us a bond order of 5. So this is how the diagram can be actually explained. And one more thing that is significant in this case is that we can see the presence of secondary interactions in this case. So usually in the case of bidentate ligands, the secondary interactions plays an important role in binding the two chromium centers tightly to each other, which helps in the formation of the chromium-chromium quintuple bonds. But in our case, these secondary interactions are not because of the presence of any bidentate ligand. Therefore, these are actually very weak interactions. And therefore these are not contributing a significant amount in formation of this chromium-chromium quintuple bond, and the length of this distance between the two chromium centers is approximately equal to 1.82 angstroms. And similar compounds have been also synthesized with the help of iron atom, and in such cases the distance between the two iron centers were actually observed to be approximately equal to 2.82 angstrom. So we can see that by the use of the same ligands for different metal centers, there was a difference in the bond lengths, which is the difference between this length and this length is found to be approximately equal to 1 angstrom. Therefore it proves that this ligand interaction, the secondary interaction, does not play a significant role in shortening the chromium-chromium bond length as compared to this iron center. And the prime reason because of this short bond length is because of the 3d5 electronic configuration of the chromium metal. And with this I come to end of my presentation. Thank you very much.